I'm Michael Davis, and welcome to my video report for Lab 1. In Lab 1, Constant Velocity, we observe the motion of some object that is moving at the same speed without changing direction. We are using Newton's second principle, known as the momentum principle, to understand how constant velocity works. As we can see here, the net force equals a change in momentum over the change in time. And we can derive the formula to see that the final velocity equals the initial velocity, plus the net force divided by the mass, times the change in time. When the net force is zero, the ending velocity is the same as the starting velocity. This is known as a constant velocity. In the experiment, I recorded a video of a fancy golden water bottle cap rolling across the table. In Tracker, I analyzed the video and recorded the object's position frame by frame in respect to that time. I made sure to be careful about setting the origin and the x-axis along the path of the bottle cap to ensure that our data records properly. We could see that recorded data in the lower right-hand corner of the tracker screen, from which we will export and plot the data. I also made a computational model of the experiment using Python code on glowscript.org. The link to this code is in the description of this YouTube video. In order to create a computational model, I have to use several key pieces of data from the experiment. My observation start time was 0 seconds. The last observation was at 1 second. The cap's initial position was 0, negative 0.0010, and the cap's mass was 0.04 kilograms. To find the initial velocity, we need to look at two positions and the time in between. Average velocity equals a change in position over the change in time. And taking the initial position and the position right after it, I calculated for an average velocity of negative 0.3367 meters per second, or 0.3367 meters per second in the negative x direction. Taking all of this information, I plugged it into the provided starter code for glowscript and ran the program. We can see that the computational model looks very similar to the real video, and we can also see our plot for position and the plot for velocity, which looks like constant velocity. This computational model acts as a predicted position versus time, and we can take the data and plot it on the same graph as the observed position versus time to compare. As we can see, our observed data, the blue dots, line up very closely with the predicted data, which is the black line. In this graph, our time is a horizontal axis, and our x position is a vertical axis, so as time progresses, our cap moves to the negative x position. Remember when I was talking about our velocity being negative? That is because in the original video, the cap rolls to the left, and since I made the origin the starting point of the cap movement goes toward the negative x direction on a graph. If I would have rolled the cap from the left side of the screen to the right, then I would have put the origin on the left, making the cap's movement away from the origin, resulting in a velocity in the positive x direction. Looking at our comparison plot, because our x direction is the vertical axis, our data points on a downward slope. But if I had the cap roll toward the positive x direction, then the slope would have gone upward. If you look closely, you can see that the blue dots do not perfectly stay on track on the predicted position. While it starts right on the line, since we based our prediction on the initial velocity, it dips a bit below the line near the middle of our interval. There are many reasons why this could be so. The bottle cap could not be perfectly circular, or the table could not be flat, causing slight variations in the velocity of the cap. The cap was very light, so it is possible that there could be wind resistance. Maybe it didn't roll it perfectly parallel to the camera, and it could have diverted slightly on the z-axis toward or away from the camera, although I took special care to make sure the roll was as straight as possible. Also, you can't forget about the forces. These forces included the weight of the cap pushing down, the opposite force of the table pushing back up, and the force of friction. The driving force created by the original force, and its opposite force of friction. While there are many other tiny forces that we cannot measure, these main forces all cancel out to equal 0. My observations lined up very well with the computational model's prediction, so we can assume that the net force was at 0 or very close to 0, resulting in a velocity that is constant. Thank you.